Okay, so welcome everyone to this week's seminar. We're very happy to have Soheil Kolouri talk this week. So Soheil is Assistant Professor in Computer Science at Vanderbilt University, where he runs the Machine Intelligence and Neural Technologies Lab. I can't read my handwriting, sorry. So before that, he was a research scientist at HRL Labs, and before that, he did his PhD at Carnegie Mellon University, which is how we actually know each other. Whilst at Carnegie Mellon University, Soheil won a couple of awards, so including the I think it's the Bertucci Fellowship for Outstanding Graduate Students in Engineering in 2014, and the Outstanding Dissertation Award in Biomedical Engineering in 2015. So we're very happy to have him here this week. He's going to talk about Wasserstein embeddings in the deep learning era. So over to you, Soheil.
Thank you so much, Matt. It's a pleasure to be here talking with you about some of the recent work that we've been working, as well as some of the old work that we've done regarding Wasserstein embeddings. So let's start. Well, I don't think I have to say that machine learning is really has become a disruptive technology, and because that's the reason we are all here talking about it. But just a few of the success stories of the machine learning in the industry, like in the healthcare, for instance, we know that today we have diabetic retinopathy detection better than the accuracy of humans, and we have augmented reality microscopes and real-time detection of cancerous regions from pathology images, and detection of breast cancers from mammograms and so on. And also in transportation, we know that self-driving cars are almost a reality, and they all rely on computer vision and machine learning. And also, like on the energy front, or smart grids and Internet of Things are more and more depending on the machine learning infrastructure. But going beyond the specific applications and looking at the core ideas in machine learning, we can see that measuring dissimilarities between distributions is a common thread behind many of these machine learning techniques. Whether we talk about one-dimensional probability densities like histograms, we talk about 2D and 3D distributions like shapes and images as they commonly appear in the medical domain, which is very close to my background. Or we can be talking about high-dimensional distributions like distribution of sensor data and images or text. And in many of these applications, we would like to be able to reliably measure the distance between the different distributions and measure a distance or a dissimilarity between distributions. So two of the applications or areas of machine learning that closely rely on estimating such dissimilarities are the density estimation and deep generative modeling, where you have a parametric distribution and the true distribution of the data, or samples from the true distribution of the data, and you would like to minimize the distance between these distributions. Okay, but we already have a lot of dissimilarity measures between distributions. And why should one care about like looking into more of these dissimilarities? And here I'm including a short list of such dissimilarity measures. For instance, the Minkowski metrics, symmetric chi-squared, Hellinger distance, Jensen-Shannon divergence, and in general, I can talk about phi divergences. And these have been studied in the literature and have been used in the literature significantly. And these dissimilarities are great when we want to compare distributions bean-wise. For instance, for the distributions shown here, the blue, green, and orange distributions, because these the dissimilarities are measured in a bean-wise manner, we are going to get that the blue and green distributions are more dissimilar compared to the blue and the orange distributions. Right. So while this could be fine for certain applications, if there is actually a meaning, a geometric meaning in our domain, we see that the green distribution is simply a shifted version of the blue by one bean, and maybe we need to seek distributions that are going to tell us something else, that tell us that the blue and green are more similar than the blue and orange. So, but let's look at a simple example to further motivate the need for a new distribution, new dissimilarity measures. Consider distributions P and Q, where Q is simply a shifted version of distribution P. And if we plot the dissimilarities between P and Q as a function of the translation parameter, then we will see that all these dissimilarities are going to return a maximum value whenever the domains of our distributions are disjoint. So this has two implications. First is that the underlying geometry of the space is not taken into account at all. And for instance, here, the three distributions that I'm showing, they all have disjoint domains. And all these dissimilarities are going to tell us that these distributions have the same, are as dissimilar from one another. And so this is not good. And then the second implication is that if we want to do a minimization for minimizing the dissimilarity between distribution P and Q as a function of the translation parameter tau, we are going to use gradient descent, for example, to solve this problem. If our initialization is unlucky and we are in a disjoint setting, then there is no gradient information for our gradient descent to match these two distributions. Okay, so but if you look at the Wasserstein distance, or in general integral probability metrics, like other integral probability metrics like maximum mean discrepancy, MMDs, they provide dissimilarity that looks like that, in the sense that you actually have sensitivity about how far the distributions are from one another. And these distances capture, the Wasserstein distances in particular, capture the underlying geometry of the space and are suitable for that. So I haven't told you what the Wasserstein distance is. Many of you might already be familiar with them, but just let me tell you the main idea. And the main idea is that as opposed to comparing distributions in a beam-wise manner, we would like to compare distributions in a cross-beam manner, okay? And on the top, you see what we mean from beam-wise, and on the bottom, you see what we mean from cross-beams. Okay. So this is just a little motivation of like why probability metrics are important, and why we would like to look into Wasserstein distances. Here's the outline of my talk. I start by providing a brief introduction to the optimal transport problem, for those of you who might not be familiar with the topic, and Wasserstein distances. And then I'll talk about the concept of Wasserstein embedding, or a linear optimal transport. And then I finally talk about the Sliced-Wasserstein embeddings and Sliced-Wasserstein distances and their variations. And for each of these topics, I'll provide some of the results that we had, published results that we had on the topic. So what is the optimal transport problem? As the title of this section implies, 18th century math for modern machine learning, optimal transport is an old mathematical problem which gives rise to the Wasserstein distances commonly used in modern machine learning. So the optimal transport problem goes back to the French mathematician Gaspard Monge in the 18th century. Monge was studying the problem of how to transport soil during the construction of the building of forts and roads with minimal transport expenses. But abstractly, this problem is equivalent to finding the optimal matching or permutation that provides the cheapest transportation cost between a set of point xi's and a set of point yj's. So we would like to find sigma that tells us which xi is going to be matched to which yj. This problem can be written as the following optimization, which we are looking at given a transportation cost d. We are looking at the average transportation cost of matching xi's to yj's, and we would like to minimize these expected transportation costs. Of course, this is a combinatorial matching problem, and it's not easy to solve. But the good news is that many years later, and in the 20th century, Kantrovich, who was a Soviet economist, was studying the supply and demand problem, and he relaxed Monge's optimal matching problem, and not at the time he wasn't aware of Monge's work, but he essentially introduced the idea of soft assignment. In Cantor's formulation, points were mass particles with different weights and could split and redistribute to solve the transportation problem. So Monge's permutation sigma became the transportation plan gamma, which tells us how much mass is being transported from location xi to location yj. So if you look at the optimization or the Cantor-Bridge problem, what we're optimizing is, again, the expected transportation cost, and this time with respect to the transportation plan gamma ij, which we can think about it as a joint distribution. And the constraints of this problem are telling us that no mass should be created or destroyed during this process. Okay, well, optimal transport is actually a versatile theory and not limited to the discrete setting. Both Monge and Cantor-Bridge formulations can be formulated in the continuous domain. And in particular, Monge's transport map becomes, the sigma that we saw in the previous slide becomes a push forward F, and the optimal transport problem becomes finding the minimum expected cost of transportation with respect to a push forward F, and finding such push forward that minimizes the expected transportation cost. And similarly, Cantor-Bridge's transportation plan turns into a joint probability measure, here shown as gamma, and the problem is again to find the minimum expected transportation cost. Okay, but one of the main appeals of optimal transport, especially from the machine learning point of view, is the concept of Wasserstein distances and the fact that we can extract distance for probability measures from the optimal transportation problem. Essentially, the Wasserstein distance between two distributions is equal to the minimum transportation cost for morphing or transporting one distribution into another. Okay, so here is the Cantor-Bridge formulation that we saw, the Cantor-Bridge formulation of the Wasserstein distance. And if our distributions are continuous and smooth, we can similarly obtain the Wasserstein distance through the Monge's formulation. But okay, so let's see an example to better understand this problem. Let's consider the two images of faces shown here as two-dimensional probability distributions. So what I mean is this is essentially a two-dimensional PDF. These images sum to one, and now we have two of them. And we would like to solve the transportation problem. And here we are going to use, say, the Monge solver, or like a solver for the Cantor-Bridge or Monge. That's okay. What we are going to get out of it is the Wasserstein distance. But maybe more importantly, we are also going to get a transportation map that's going to be the push forward from one measure to the other measure. Okay, so but this transportation map in a differential form, we can write it as like a determinant of the Jacobian of f times q evaluated at f is going to be equal to our source measure, which was p, or distribution that was p. For those of you who are familiar with image registration, like the term Q of F is essentially performing an image registration, while the determinant of the Jacobian is ensuring mass preservation. But maybe more importantly, beyond just ensuring mass preservation, it's allowing us to change the texture and model the texture variations on images as well. Okay. Now that we are equipped with metric, we can talk about things like geodesics or shortest paths between two distributions. So if you think of the space of probability measures here shown in yellow, and if you have two distributions P and Q, then the shortest path between these distributions in a Euclidean setting is of course going to just be the straight line connecting them. And the shortest path in the Wasserstein distance is going to give us the Wasserstein geodesic here shown as a curve. And it turns out that the geodesic for the two Wasserstein distance can be calculated and is parameterized as the push forward of the source measure with respect to a convex combination of identity and the optimal transport map. Okay, so what are the implications of these geodesics? So if we compare the two Wasserstein geodesic with the Euclidean geodesic, we clearly see that the nonlinear modeling effect caused by optimal transportation or the transportation problem in the Euclidean geodesic. Here we have distributions, the source distribution, the target distribution shown out there, and same thing. And we are looking at the Euclidean geodesics versus the Wasserstein geodesics. And we see that in the Euclidean geodesic, mass is being destroyed in one location and created, teleported in the other location. Same for the 2D and more complex distributions. And while in the Wasserstein geodesic, we see the transportation effect that we're actually transporting mass from one location to another location, which can be thought as a nonlinear modeling of the distributions. Okay, and it's very important for image analysis applications, because the average in the Wasserstein case doesn't suffer from this ghost effect, which you can see two eyes or two faces showing up at the same time, while you see a smooth transition for the Wasserstein geodesic. Okay, so to put it all together, this was like very fast primer on optimal transport, but optimal transport allows us to compare distributions in a geometrically meaningful manner, given two distributions and a ground metric, D. Solving the optimal transport problem provides us with one, the optimal correspondences between the distributions. In other words, it solves the optimal matching problem between the samples from the two distributions. It provides a metric between the two distributions, which again is different from the ground metric. This is a metric between the distributions and not the samples. And also it allows us to interpolate between different distributions in a nonlinear fashion, right? Like by calculating the geodesic. So this is an image that I personally have in mind when I think about optimal transport in a lot of the applications. So far I have told you a lot of good things about optimal transport and Wasserstein distances, but the caveat of this distance is that the transportation problem is computationally expensive to calculate. So generally the linear programming problem, which is the Cantor-Rich optimal transportation problem, is supercubic in the number of mass particles to solve. So it's order n cubed log n. And there are, of course, there has been a lot of work on how to make this faster. Like Marco Couturier has this Sinkhorn distances, which are the entropy regularized version of this, which reduces this complexity to quadratic. And there has been more and more studies to make this faster. But going with just the general case of the supercubic, there are problems with this. And the problem is if we want to calculate, say, pairwise distances between a set of m probability measures, we need to calculate m squared of such distances and to do any modeling on our probability distributions. And m squared of n cubed log n is very expensive. And the other problem is if you want to do gradient descent, for example, to minimize or Wasserstein distance between two distributions, this is again problematic because if we want to calculate, we have to calculate essentially a supercubic optimization in each step of our gradient descent. Okay, so this brings us to the idea of Wasserstein embeddings or linear optimal transport to help us reduce this computational burden a little bit. Here, this work was mainly done with Gustavo Rode and Dejan Slepčev at CMU. So, and the idea is that reduce the computational complexity from m squared, where m is the number of probability distributions we have in a data set, to m. Okay, so that's a significant reduction in computation. And so let me motivate the concept of Wasserstein embedding through a biomedical application. And essentially when we started with these ideas, we were studying predictive modeling of cancer in liver tissue by considering the chromatin content of cell nuclei. So we had whole slide pathology images from which we had segmented the nuclei, and then we had data from two groups which were which had benign and malignant types of liver cancer. So the chromatin concentration in each nucleus can be treated as a two-dimensional distribution. So each image we treat it as a PDF. And then the two questions we wanted to answer her, the first one, are there differences? Of course, this is a very a question that machine learners and statisticians really like, and we can usually find an answer to this question. Yes, there are statistical differences between these two groups, but more importantly, what are the differences? And we wanted to be able to answer like what are the distributional variations? So model the variations of these distributions between these two groups. Okay. We were inspired by the research in the field of computational anatomy, where shapes are registered to a reference shape, and the statistical analysis is performed on the registration maps as opposed to the shapes themselves. But there are two caveats with this approach for the specific application that we had, which was to analyze the distribution of the chromatin in cells. And the caveats were, the first one was the registration map calculated is usually not unique. So you can, and you need to essentially carefully regularize the registration problem to enforce some sort of uniqueness. But maybe more importantly, these approaches cannot handle texture variations. They're mainly developed for shape analysis. But being familiar with optimal transport, at the time we thought, okay, can we use optimal transport maps that are unique? And also they can model the texture variations for these cells. And so the idea is then to calculate the transport map from or distributions to a reference distribution. And then we can think about this process as an embedding process. Given a fixed reference, we can send an image in, a two-dimensional distribution in, and calculate the transport map. But this embedding is invertible also. We can get that transport map and send it through our inverse of this embedding, which is a push forward and pull back essentially, and recover the original distribution. So we can show that the Euclidean distance between, so thinking about this as an embedding, then we can show that the Euclidean distance between the embedded distributions, which are the transport maps, are actually an approximation of the Wasserstein distance, the two Wasserstein distance between the distributions. So with this process, what we have is an approximate Euclidean embedding for the Wasserstein distance. And then the idea is to transform or distributions to this transport space or to this embedding space, and then perform analysis there, discriminative or explorative analysis in this embedding space, and then inverse these transformations and visualize everything in the image space. Okay. Of course, I said that this is an approximation, and then the natural question here is like, what is the approximation error? And Caroline Nussmuller and Alex Cloninger had a wonderful paper that studied this embedding very closely and provided some answers about the approximation error. So just to put it in a nutshell, they showed that two measures, if two measures mu I and mu j are push forwards of a fixed measure mu on their shifts and scalings, then this embedding is isometric. So the Wasserstein embedding is an isometric embedding. So the Euclidean distance is exactly equal to the Wasserstein distance. And then maybe more importantly, the embedding is near isometric if two measures are push forwards of a fixed measure on their mappings belonging to an epsilon cube, epsilon tube around the set of shifts and scalings. So, so this gives us some sense of the approximation error for the Wasserstein embedding. Okay, so now let's see some examples of how this embedding works in practice. Say we have a fixed reference measure, and then we have inputs II and ij. These are our PDFs, probability distribution functions. So we calculate the Monge maps to the reference, and then we get Fi and Fj, and this is essentially our embedded distributions. And then we perform a convex combination of these transportation maps, Fi and Fj, and we perform also the convex combination of the images to generate the Wasserstein geodesic. Actually, this is not the Wasserstein geodesic, but the Euclidean geodesic in the embedding, as opposed to the Euclidean geodesic in the original space of the measures. So, and then we can, after that, we can essentially apply that pull back to a reference and visualize the calculated Euclidean geodesic in the embedding space and the Euclidean geodesic in the original space. And we see that we get similar effects as the actual Wasserstein geodesic by calculating the Euclidean geodesic in the embedding space. So this is another example where the inputs are not images, but the inputs are two-dimensional samples from essentially two-dimensional distributions. And so each distribution is simply a ring with some noise added to it. And they are shifted and scaled versions of each other. They have different number of samples in them. And this matches the theory behind the approximation error really nicely, because they actually, all the distributions here are generated by an epsilon tube around the shifts and scalings. Okay, so now here the reference measure is actually an arbitrary normal distribution, samples from a normal distribution. And then to embed the one distribution into our Wasserstein embedding, we calculate the Monge coupling. We calculate the contribution problem and then do a barycentric projection to get an approximated Monge map. And then we use this approximated Monge map as the embedded distribution. So then if we do calculate the mean in our embedding and apply it to a reference, what we get is the mean distribution as expected in a ring. And also we can calculate the geodesics from the Euclidean geodesic in the embedding space from the reference measure to any of these measures. And you see how that is happening here. And also between two different measures. And we can see that you get something that's very close to, at least qualitatively, it's very close to the Wasserstein embedding. Okay, so these were some toy examples. Now we can go and talk about some more interesting examples. Going back to the chromatin distribution in cell nuclei, we have the two groups in the image space, and then we map these images to the transport space, to our embedding space, where each distribution becomes a transport map. And then we perform parametric learning on the training sets. Here, in this case, we use simply linear discriminant analysis. And we obtain the discriminant direction. And then this is going to tell us whether we have found something that's statistically significant, then applied to our validation set. And but moreover, we can essentially calculate the inverse of this embedding and visualize everything in the image space. And that's where we get this nice explanation of what is a discriminative behavior between different, the distribution of different nuclei. Okay. And here, for example, we see a migration of the chromatin from the periphery of the nucleus toward the center of the nucleus. And this is the main cause of variation between the two groups. But beside discriminative analysis, we can perform exploratory analysis of the data, say by applying principal component analysis in the transport space or in the embedding space, and then inverting these principal components back to the distribution space and visualize the variations. And that's exactly what we've done. Each column here shows one of the principal components, and you can see that we get these variations in this data set really nicely. We can model the variations in this data set really nicely. Okay, here is something that's a little bit more exciting and more interesting. If we look at the percentage captured energy of the principal components, we see that our embedding essentially provides, captures the variations in our data set very nicely compared to some other transformations that we applied, like radon space, regional space, and image space. So this embedding is beneficial computationally, but it's also buying us a lot of modeling power for two-dimensional distributions in this case. So knowing that the idea worked for two-dimensional images, we extended it to 3D images and applied it to CT and MRI images. And our work was published in NeurIPS 2019. But like here, for example, what we're looking at is two classes of brains based on persons with low fitness index and persons with high fitness index. Similarly, we treat the volumetric brains as three-dimensional distributions. We have a reference measure, and then we calculate the transport maps to that reference measure, and then do our analysis on the transportation maps and invert everything and visualize things in the original space. I'm not a neuroscientist, but even I can see that there is a difference between, like, for example, the ventricles from the least fit person to the most fit person. And this is very nicely captured through this Wasserstein embedding framework. Okay, so let's kind of recap of what we've done so far. I started by saying that we need better probability distances and dissimilarities, and then talked about optimal transport and Wasserstein distances, and said that they are computationally expensive, unfortunately. And one way to reduce this computational expense, not for the calculation of the distance, but for performing machine learning on the for M probability distributions, is to use this idea of Wasserstein embedding that reduces the complexity from M squared to M. And the applications that we have seen so far are two-dimensional images, specifically pathology images, and three-dimensional images. So now the natural question is, can we do it in n-dimensional distributions in general? And this is a work that I've mainly done on in HRL laboratories with my collaborators Navid, Heiko, and of course, a continued collaboration with Gustavo, who's fantastic. So let me tell you what we did. So essentially, we used this idea of Wasserstein embedding for learning from graphs. And I'm first going to tell you like why we got interested in graphs. And the reason is, of course, like a lot of the signals and images and videos that we work with live on regular data structures, live on grids. But there are a lot of other data points or data types that don't live on regular grids, like social networks, data, communication systems, molecules, and so on. And we had applications that essentially dealt with this irregular type data. And we wanted methods for those. Of course, there are graph neural networks and graph kernels as two common approaches that are used in the literature currently for performing learning of graphs. But let me tell you the very high level idea behind these approaches. So given two graphs, there is a process of node embedding. So what happens is this process involves some sort of local feature aggregation and combining the local features in order to get some more context level features for the graph. And then at the end, at the end of this process, this node embedding process, you have features that represent each node. And then you would like to do learning on this. But of course, you can have graphs with different number of nodes and so on. And then because of that, this process is followed by a general pooling, for example, an average pool. And then these averages of the node embeddings are sent to downstream tasks, classification, regression, so on. And this process is learned end to end. Okay. But here, something that's interesting is that essentially by taking this average, we are stating that there is a distribution, and we are thinking that this distribution can be represented with its first moment, right? With simply its mean. So we were actually looking into this when an interesting paper came out by Tony Nolly et al. In NeurIPS 2019. And they said, yes, we can think about the node embeddings as empirical distributions. And instead of just taking the global average pool, we are going to calculate the Wasserstein distance between the embedded nodes of different graphs. And based on this Wasserstein distance, by calculating a contribution problem, for example, we can define a similarity kernel, simply e to the negative lambda of the Wasserstein distance between the node embeddings. And then use this graph for any machine learning problems, for like kernel SVMs and so on. Okay, treat this as a kernel for graphs. Okay, great. But then you need to calculate essentially M squared Wasserstein distances. And this is a very natural application for Wasserstein embeddings. So instead of calculating the pairwise Wasserstein distances, we said, okay, we have this Wasserstein embedding, we can simply apply it to distributions of the node embeddings, and then use the embedded points and send them to downstream tasks for classification, regression, or any other or whatnot. Okay, so here's the idea. We do the node embedding, and we have a reference distribution, and then we calculate the approximated Monge map between the reference and the node embeddings, and then the transport displacements are used as the embedded data, as the embedding for downstream tasks. So the idea is pretty simple here. But then the gain that we have is that for a data set of M graphs, we require only M calculation of the optimal transport problem, while the previous work was using M squared. And we showed that we are actually not getting any reduction in performance by doing so. And so we tested our algorithm on two different benchmark data sets. First is the OGB mole HIV data set, which is a data set of molecules that can inhibit the HIV virus. And it's a binary classification. You need to predict whether this molecule can inhibit HIV virus or not. And so we compared our method with many of the state-of-the-art in the literature, and we performed really well. So at the time, we provided like one of the highest performances on the data set, on the leaderboard for this data set. And also we showed that for other benchmark data sets, like TU data sets, we were able to perform really well compared to state-of-the-art graph neural network and graph kernel algorithms with this simple idea. But maybe more importantly, we showed that we can essentially maintain performance or improve the performance by keeping the computations very low. So both our training time and inference time are significantly lower than the state-of-the-art methods. So this work was published in ICLR 2021, so this year, earlier this year. Okay, so we saw what Wasserstein embedding, what Wasserstein distance is, and then we saw that Wasserstein embedding is essentially going to allow us to reduce the computation from m squared n cubed log n to m n cubed log n. But then we can essentially push the calculation of the Wasserstein distance itself and reduce this n cubed log n to something else. And that's something else that is interesting to us, and we have been working on it a lot lately, is the use of the Sliced-Wasserstein distances. So as opposed to using the Wasserstein distance, if we use the Sliced-Wasserstein distances, we can calculate the Sliced-Wasserstein distance in kn log n and get a significant reduction just simply using the Sliced-Wasserstein distance. But on top of it, if we use the Sliced-Wasserstein embedding, we get double benefit, and we get kmn log n for performing any analysis. Again, m is the number of distributions, n is the average number of samples per distributions or particles per distributions. So the last part of my talk is about this idea of, yeah.
Can I ask a quick question? So K here, is this the number of directions in the Sliced-Wasserstein distance?
Yes, K is the number of slices, exactly. And we're going to explain what that is exactly, yes. Okay, so I told you that Wasserstein distance is computationally expensive, but actually in one dimension, when our PDFs are one-dimensional PDFs, this is not the case. The optimal transfer problem has a closed form solution, and the Wasserstein distance can be calculated in n log n, okay? And how it's calculated is simply like the Minkowski distance between the quantile functions, and quantile functions are the inverse of the cumulative distribution functions, okay? So, so in one dimension, they are easy to calculate, but the problem is in one dimension, like one-dimensional problems might not be as interesting. Like we are interested in higher dimensional probability distributions. And this is where integral geometry comes to our rescue. So integral geometry from the results of radon, we know that we can represent a d-dimensional distribution as a collection of its one-dimensional slices. And these one-dimensional slices essentially provide all the information we need to represent our distribution. In another word, like we can always recover the distribution from its slices. So what are these slices? I use the term slice, but I never defined it. Well, a slice here is simply defined as an integration of the distribution over hyperplanes orthogonal to a unit vector theta. Okay. An example here is shown as a two-dimensional distribution. You select a theta. Theta is a direction in a vector belonging to the unit ball, and then you simply integrate the distribution along all the hyperplanes orthogonal to your theta, and then you get a one-dimensional distribution out of this. So this is going to be one slice. And if you keep doing it for different thetas and you do it for infinite number of thetas, then this process is an invertible process. You can recover your distribution from these one-dimensional slices. Okay, and this is an idea that's used in computational tomography. This is the bread and butter of computational tomography, right? So now we can combine these two ideas. The one-dimensional Wasserstein calculation is easy, and then we can slice high-dimensional distributions and define the Sliced-Wasserstein distance. And so the Sliced-Wasserstein distance is essentially calculating the expected Wasserstein distance between the slices of two distributions. So for two distributions, we slice them with respect to the same theta. We calculate the Wasserstein distance, and then we calculate what is the expected Wasserstein distance for all possible thetas. The first question, is it a true metric? The answer is yes. It satisfies all metric criteria. And then maybe more interestingly, it's topologically equivalent to the Wasserstein distance. And we had a NeurIPS 2020 paper that we studied in depth, like topological and statistical characteristic of the Sliced-Wasserstein distance. And there has been a lot of work since then on showing these relationships as well. Okay, so computationally, what are we gaining here? Because of course, this is still an integral over an infinite number of slices. Well, we can approximate this integral with Monte Carlo integration and use only k slices to represent that integral. And then computationally, what we gain from this is if you're using parallel processing, we can essentially slice in each processor, we can slice the distribution with respect to, essentially pick a theta first, then slice the distributions with respect to that theta, and then calculate the Wasserstein, which is n log n for these slices. And then at the end, get the output of all the processors and just simply average them. And that's going to give you the approximation of the Sliced-Wasserstein distance, the Monte Carlo approximation of the Sliced-Wasserstein distance. And that's why it's the computational complexity is k n log n. Okay. And actually, like, yeah, so let's next slide. So I wanted to just briefly mention that using the theory of generalized radon transform, we can essentially treat these slices not only on integration over hyperplanes, but we can have integration over hypersurfaces. So substituting the inner product in the radon transform with a general nonlinear function going from our D to R, gx theta, given that this G satisfies certain characteristics, which we detail in our NeurIPS 2020 paper on generalized Sliced-Wasserstein distances, we can essentially have the slices that are defined by integration over hypersurfaces as opposed to hyperplanes, which opens a new door essentially of asking many interesting research questions on this slide. And then we can similarly define the generalized Sliced-Wasserstein distance as the expected value of the Wasserstein distance over these nonlinear type slices, just as a side note. Okay, so going back to the familiar problem of essentially having two distributions P and Q, and the Q is a translated version of P. If we calculate the dissimilarities that we have seen before, the phi divergence type, Minkowski, Hellinger, and so on, we see that whenever we have disjoint domains, we have the highest value. And of course, we saw the Wasserstein distance doesn't behave like that. And then we see that the Sliced-Wasserstein distance is behaving very much similar to the Wasserstein distance. So that's good. Okay, so that's a Sliced-Wasserstein distance. Then now, what can we do? So this was a Sliced-Wasserstein distance. What can we do to use the Sliced-Wasserstein embedding? So the idea, now that we know what Wasserstein embedding is actually quite simple. The idea is that we can define a reference measure, and then we have another input distribution. We can slice these measures into K slices. Here, I think I'm using L slices as opposed to K, sorry. But then we can essentially calculate the Wasserstein embedding for each slice separately. And these are going to give us a Monge map per slice. And then we can concatenate these Monge maps and generate or embedded vector. Okay. And then we can show that actually, if we have infinite number of slices, this is an isometric embedding for a Sliced-Wasserstein instance, regardless of the choice of the reference or how different the distributions are from one another. So we can see this in practice. Here I forgot to mention that, and I'm going to hopefully convey the idea that this Sliced-Wasserstein embedding is going to be really easily integrated into a deep neural network architecture and trained end to end. So we are going to head toward that direction. But before we go there, quickly, here again, I have the two distributions that we looked at before. Interpolation in the Euclidean space, interpolation in the radon space, which is like the on the slices essentially, and then calculating the inverse. We see that because this is a linear transformation, the geodesics are essentially exactly the same as similar between the Euclidean and the radon. But when we do our interpolation on the Sliced-Wasserstein embedding, we see that we have this nice transformation, nice transportation from one distribution to another distribution. And similar for faces, we can show the same thing. See how I'm doing. So I need to speed up a little bit. So this idea, we recently used this Sliced-Wasserstein embedding for modeling, for classifying images in a low label regime. Okay, so when we don't have a lot of labels, to use the Sliced-Wasserstein embedding for learning from that in that setting. So what we have in the image space are hand gestures, and we would like to be able to tell these hand gestures apart. So we treat the hand as essentially a distribution again. We treat this as a two-dimensional distribution, and we calculate the Sliced-Wasserstein embedding. Then in the Sliced-Wasserstein embedding, we do subspace modeling per class. Easy peasy. And after we do subspace modeling for the new test data, all we do is we calculate the nearest subspace classification. Okay, so for the test data, we first calculate the embedding, and then look which of the subspaces is closest to the point that we have, and then the class assignment is done that way. Okay. So some results on this. This is again a very simple idea, but we see that it provides a very strong benchmark for learning with less labels, essentially. So what we are looking at here are three different data sets: sign language that we saw the data set, affine and NIST, which is handwritten data sets, but affine transformation is applied to them, and then Chinese printed characters. And then what you see in the x-axis is the number of training samples used per class to learn the classification. And then on the y-axis, you see the test accuracy. And the curves, the red one is the proposed subspace modeling in the Sliced-Wasserstein embedding. And the other curves are showing the performance of different neural networks: ResNets, shallow convolutional neural networks, and VGG nets. Of course, when the data is limited, these methods are going to perform very poorly because they don't have much prior built in them. But the Sliced-Wasserstein embedding has a lot of prior, as we saw, the shift and translations are kind of built into the transportation framework. So because of that prior, we do much better compared to the neural networks in a low data regime for all the data sets that we studied. Okay. So the final part is, okay, so we can think about this as Sliced-Wasserstein embedding as a set to vector operator and simply integrate this into a neural net. And that's where we want to go. And this is the work done again at HRL and also my students here at Vanderbilt. Okay. So the idea of a Sliced-Wasserstein embedding we have already covered. We have an input set. We treat the set as samples from a distribution. We treat the set essentially as an empirical distribution. We have a reference set, which is a reference empirical distribution. And then we do our Sliced-Wasserstein embedding by first generating L random samples from ST minus 1. And then we do the approximated Monge map, and then keep appending these Monge maps per slice. And that's going to give us an L by M. Here, L I'm using as the number of slices. M is the number of points in our reference set. And then we have a way to embed a set into a vector, into a fixed dimensional vector. So the sets can have different cardinalities and different permutations and so on. And we are going to get a fixed dimensional representation of it. So what is this good for if we have data sets that are of the form of sets? So we call them set structured data, like point clouds are set structured data. And we would like to essentially perform classification or retrieval on point clouds. And this is a work that's going to be presented in NeurIPS 2021, upcoming NeurIPS conference. So here is some of the results that we have on our unpublished work, and I wanted to just show that we can simply use a Sliced-Wasserstein embedding as a set to vector, and then perform nearest neighbor retrieval on the embedded points for different point clouds data set. And we found that this idea is actually very powerful, and this Sliced-Wasserstein embedding works really well for this application, but I'm not going to go in the detail of this for the sake of time, and this is not published yet. It's under review currently. But okay, so what we have published is this. Say we want to learn like to do classification on set structured data, here point clouds. And the existing methods rely on two different parts, very much similar to the graph data structure that we talked about. The first part is a permutation equivariant backbone. Simply, for example, we can use a multi-layer perceptron applied to each sample, or you can have transformer networks and so on, which are significantly more complicated. But so the backbone, there is a permutation equivariant backbone, and then followed by a pooling or a set to vector operator. So that operator can be, for example, the global average mean, or can be the Sliced-Wasserstein embedding, okay? And if you put a Sliced-Wasserstein embedding here and then send the fixed dimensional vector for any downstream task, something interesting happens here. We can actually optimize in an end-to-end manner, both on the reference set and on the slices. So we don't need to just pick random slices, we can optimize our slices to find the ones that best describe the characteristic that we want to get at the end. For example, being a discriminative embedding for different classes of data. Okay, so this is done end to end. And here are some of our results on classification of point cloud data, comparing simply for two different backbones, a multi-layer perceptron and in ISAB is a transformer network. And then performing GAP, which is global average pooling, as opposed to performing a Sliced-Wasserstein embedding, a different number of slices, L from one slice up to 1024. Of course, we're in a three-dimensional space, or point clouds live in a three-dimensional space. And I want to point out something really interesting here. So GAP actually performs very poorly when our backbone is very simple. When our backbone is a multi-layer perceptron applied to each sample of our point cloud, it performs really bad. But then when our backbone becomes more complicated, like a transformer network, it starts working really good, really well. Okay. But then our Sliced-Wasserstein embedding really doesn't care much about how complicated the backbone is, because it's doing a lot of the modeling of the distributions as the process of the vector embedding. And we see that even with a simple backbone, multi-layer perceptron, what it's doing is providing results that are on par or better than a transformer backbone compared with a global average, followed by global average. And also we see some gain if you increase the complexity of your backbone, we get some gains in performance, but this gain is not as big as it is for gap. So that's essentially like where this Sliced-Wasserstein embedding could really shine is when we don't have enough resources to have a very complicated backbone. Okay. So given that we're almost at the end, I just want to briefly put together like what to remember from this talk. So we started by saying why we need better probabilities. We talked about optimal, probability distances, and then we talked about optimal transport problem and Wasserstein distances, and then followed by Wasserstein embeddings for 2D, 3D, and ND distributions. And then finally, we talked about the idea of a sliced Wasserstein distances and how integral geometry can help us make faster approximation to the Wasserstein distance. And finally, we talked about the Sliced-Wasserstein embedding and how that can be integrated in as a set-to-vec operator in deep neural networks. So with that, I would like to thank all my collaborators who've been wonderful and contributed to this work. And this talk wouldn't have been possible without them. And if you're interested in any of the papers and codes, please visit our lab's website, which is vanderbilt.edu/netlab. Thank you.
I have a quick question.